Hello, so we just left off with the fact that I could take any old regular quadratic equation and rewrite it in these terms, a times x minus h squared plus k. And so here I have a version of a graph like that, where a is 1, h is 0, and k is 0. And if you work out all the algebra related to this, what this boils down to is the graph y equals x squared, which, as we know, is just a regular parabola. Now, you may remember certain things about parabolas. It's always non-negative. It's symmetric, so the values on the positive side, like 2 and -2, both give you the same value 4, and 3 and -3 both give you 9. Let's move it up a bit here. And it would be nice if essentially the graph of any quadratic equation gave you the same things. So what I want to sort of point out here is that this h, this k, and this a, they play very specific roles. And I want you to think of all of those things as some modification of x squared. So right now, this is the graph of x squared. That's what happens when h is 0 and these other two parameters are what they are. What happens if I change h? So if I make h a positive value, what's going on here is that I'm taking my x values and I'm subtracting some value, in this case 3, from it. So the way we can think about that is the graph y equals x squared, except that the x is delayed by 3 units. I'm taking my x values and I'm subtracting 3. So everything that used to happen, say at 0, now happens at 3. What used to happen at -1 is now happening at 2 instead. Everything gets delayed by 3. If I subtract a negative number from h, in other words, I add a positive value to x, that's like speeding things up by h units. So in this case, I have x minus -4, x plus 4. So everything is occurring 4 units sooner than they would have before. So this h just takes the same x squared graph and just shifts it left and right. So let's put that back on the 0 here. And let's talk about what happens when we change k. Well, k just adds some value to what we have here. So if I make k positive, I raise the graph up. If I make k negative, I bring the graph down, right? I'm just taking all of the y values and I'm adding k to them, or I'm subtracting k from them. So either way, they just shift the original parabola up or down. Now, if I combine these things, all I'm doing is shifting the locus of my parabola around the space. And so finally, what does changing a do? Well, right now, a is 1, so what I'm getting is x squared. If I multiply x squared by 2, what's happening is everything's getting doubled, so everything's getting stretched up twice as far. So any height here now goes up twice from where it was. And the more I stretch it, the thinner it gets because it's being pulled upwards. I can flatten it by multiplying by values less than 1. And so, for example, if this is 0.2, then everything's shrunk down by a fifth, and I've flattened out my parabola here. And the same thing happens if my a is negative. All that's happening when I make my a negative is that I'm flipping things over. So if it's really, really, really negative here, then it's been flipped over and stretched out. If it's between -1 and 0, then it's flipped open and flattened, right? And we can compare that to just the reflection y equals minus x squared. Let's change that color. Right? It's flattened compared to that. But the point of all of this is that every parabola we showed, or every quadratic equation, is something of that form. And so no matter what craziness that you might get in terms of A, H, and K, all you're going to get is some stretched out, shifted around version of the original x squared. So it's going to have all the same properties. It's going to be symmetric around its highest or lowest point, depending, right? And it's all of them are going to fundamentally have the same shape, which is the shape of a parabola. So another thing that you might want to use Desmos for is to solve um, for the zeros or solve for the equations of a parabola. So let's say that y equals ax squared plus bx plus c. Let's add all of these things in here. Let's not do something like that. Let's make up something from the problem. So example 8 from your book says that you have a revenue function that's minus x squared plus 30x. Let's kill these. And that's a revenue function. And so if I zoom out here, it's something that looks like that. And that you have a cost function, a c of x, that's 5x plus 100. So certainly you could on paper set this equal to that, subtract one side from the other, and use the quadratic formula or factoring to solve for when your revenue exceeds your cost. But if I graph these two things side by side next to each other, what we'll see is that when we produce between what it looks like 5 goods and 20 goods, that those are the values where your revenues exceed your costs. And so this part of the graph here is where you have positive profit, and at these 2 points are where you break even. And in fact, we could just as well graph a profit function, which is your revenue minus your costs. And if we do that, then that's exactly what we see. Between 5 and 20, we have, or at 5 and 20 are your break-even points. We lose money outside of that, but between 5 and 20, we make money, and that's maximized at when x is 12 and a half. And so using the technology here to give a visual representation of what's going on is a very useful way to go about solving problems like this.